The first topic for this week is forced periodic vibrations. So last week we saw how a spring behaves with only damping and gravity being applied to the spring itself. So how if you displace the spring from its stable position, it's going to try to get back to its stable position, and if you have some damping, that will actually get it there, otherwise it starts a periodic vibration. And here we want to look at forced periodic vibration. So we have the system that we studied last week, and we add an external forcing. So what we had last week was this system of a mass that is undergoing gravity, that is being pulled back by the spring to its stable position, and that is slowed down by damping. And now we add a forcing term. This forcing term doesn't depend on u, but only depends on t. So for example, we could have something like u second plus u prime plus 5 over 4u equal 3 times cos of t. And we have some initial conditions like u at 0 is equal to 2 and u prime at 0 is equal to 3. What behavior does this system have? Now it's a second order ODE with a non-homogeneous term. So we know how to solve this. The first step is to solve the homogeneous solution. And we can do this through a characteristic equation approach. So we replace u by coefficient times exponential of RT. Then we simplify the coefficients away, we simplify the exponential away, and we retrieve the characteristic equation. So the characteristic equation for our ODE, a homogeneous ODE, is r squared plus r plus 5 over 4 equals to 0. And we can solve this because there's a parabolic equation, so we have formulas to solve this explicitly, and we retrieve that the roots of this are minus 1/2 plus or minus the imaginary number. So from this we know that the general solution of the homogeneous ODE is exponential of minus 1/2 time multiplied by a linear combination of sine of t and cosine of t. Now that we have the general solution for the homogeneous problem, we want to find a particular solution of the non-homogeneous problem. And we're going to do it with the method of undetermined parameters because the right-hand side, our forcing term, is so nice. It's just 3 cos t. So undetermined parameters work in this setting. We guess that our particular solution should be a linear combination of cos and this is a typo. Cosine and sine. One of the two should be a sine. Here, b is associated with the sine. So we start with the guess that this particular solution u should be of the form a cos t plus b sin t. And we take the first and the second derivative. Sine and cosines, we know how to do that. And we plug these values inside our ODE, so u second minus u prime plus 5/4 u. And if we do the calculations, we retrieve that this is cosine of t times something that depends on a and b, and sine of t with something that depends on a and b as a coefficient in front. We need this to match our forcing term. So we need 1/4 a minus b cos t plus minus a plus 1/4 b sin t equals to 3 cos t. That means that the coefficients in front of the cosine needs to be equal, and the coefficients in front of the sine need to be equal. The right-hand side here, the forcing term, doesn't have anything corresponding to the sine. That means that we have to put the coefficient in front of the sine equal to 0. So this one equation with cosine of t and sine of t splits up in two equations that are algebraic on a and b. So now we have 1/4 a minus b is equal to 3, and minus a plus 1/4 b is equal to 0, and we can solve this by finding explicit values of a and b. So now we have a specific solution, a particular solution of the non-homogeneous ODE. And the general solution of the non-homogeneous ODE is the sum of the general solution of the homogeneous part plus the particular solution. So we have exponential of minus 1/2 t times a linear combination of sine and cosine, plus sine and cosine with the coefficients that we just matched. Notice how sine and cosine in one case do not interact with the sine and cosine in the parentheses, because the sine and cosine in the parentheses are multiplied by the exponential of minus 1/2 t. And that is an important part. So now we have the general solution for the non-homogeneous ODE. We still have C1 and C2 that we can change in order to adapt to any initial condition that we are thrown. So for example, now we have to fix C1 and C2 by imposing the boundary conditions of the specific problem we're looking at. So we just plug them in, we take the general solution at 0, that is C1 plus 12 over 17, and we have to match it with the boundary condition, so that must be equal to 2. And the other boundary condition is u prime computed at 0, and that gives us minus 1/2 C1 plus C2 plus 48 divided 17, and that needs to match our boundary condition for the derivative equals to 3. So we have again two linear equations in two variables, C1 and C2. So we can solve for the two variables, and we only have one solution. So we have C1 being 22/17 and C2 being 14/17. So we have a full solution. We have the homogeneous part, in which now we have fixed the constant C1 and C2, and which have the particular solution in sine and cosine. Let's look at this situation a little bit longer. So the key element that I want you to look at is that this exponential has a negative coefficient in front of t. So for t tending to infinity, that exponential tends to 0. That means that everything in the first line tends to 0 for t getting bigger and bigger, because cosine and sine oscillate between +1 and -1, but they're multiplied by something that is tending to 0. So the block given by the homogeneous solution, it's tending to 0. But the block given by the particular solution is a combination of sine and cosine, so that part is not tending to 0. We call the part that tends to 0 the transient solution. The idea is that if you're looking at a system for a long time, the part that disappears doesn't matter to you, so it transient away. On the other hand, we talk about the part that stays there the whole time as a steady state solution. Now it might seem counterintuitive because it's not steady, but it comes from PDEs in which you can have steady states that don't depend on time. Think of the fact that if you were to write this as a dependency on an x, that would be accepted as a steady state. But the idea is really that there is a part that disappears in time and a part that is important and stays the whole time. So let's try to plot the transient solution and the steady state solution in MATLAB. So as you have seen, I'm going to do a live coding session, and we're going to see how to plot things in a nice way. So the first step is that we just want to create the transient solution and the steady state solution as two different functions. So I'm going to call it transient equal at t is a function of t, exponential of minus 0.5 times t times round parenthesis 22 divided 17 times cos t plus 14 divided 17 times sin t. Notice how first I made a typo and this is a plus sign, and then I'm using a dot product between the exponential and the sine and cosine. The idea is that I want to use t as a vector of possible times, and I want MATLAB to do the multiplication element by element when it's trying to match the exponential and the cosine and the sine. Semicolon such it doesn't print everything, and that is the transient part of the solution. Then we have the steady part that is again a function of t, and we have a similar format except that we don't have the exponential in front. So we have 12 divided 17 times cos of t plus 48 divided 17 times sine of t. Then the full solution is the sum of the two, but it's again a function of t. So you have to remember this at t to remind MATLAB that that is a function. So now we have the full solution. That is just the sum of the transient solution as a function of t plus a steady solution as a function of t. Then I want to plot. How do I do that? Well, first I define a time for which I want to plot. I'm going from 0 as small step sizes to, for example, 60. That should be plenty. And then I'm plotting time on the x-axis, and on the vertical axis I'm going to start by plotting the transient solution. And I'm going to see if this works. So I'm going to save it as forced vibrations. I'm going to share this code with you. Then I open the command window. I'm actually going to undock the command window to make it easier to pass from one thing to the next. And I'm going to call for forced vibration. Invalid data argument. This is because in the live script that always happens. I'm calling transient, but transient is a function, so it's not a vector as something that MATLAB can plot. So this there is a t missing. So if I save and run this again, it's not called t here, it's called time. So time is the vector, while t is the variable that you don't really see, is within the function. So now it should work. And it gives us a figure with the transient solution. So you see it starts at some values. Notice that those are not the values of our initial conditions. And it dampens out and it goes to 0 quite quickly because it's an exponential over time. So it tends to 0 very fast. And the oscillations are given by the sine and cosine part. So if you're looking at the equations again, the exponential of -1/2 t is what squishes things to 0 very fast, and the sine and cosine are what allows you these oscillations before you're tending to 0. Now let's, instead of plotting time and transient, let's plot time and steady state. Let's not make the same mistakes as before. So steady is a function, so you have to give an argument for the function. And we run forced vibrations again, and what you see here is that you have actually oscillations. So there's steady state means that the oscillations have always the same width. So it's not changing over time all that much. It's just oscillating up and down. It's a sine and cosine with the same frequency. So now that we have the steady state and the transient state, let's plot the sum of the two. So plot the time and the full solution that is again a function of time. And what you notice, let's look at this a bit bigger, is what we're expecting. The transient solution is giving a kick at the beginning, but then you only notice the steady state solution. So this part, quite soon, actually, not at the end of the plot, quite almost immediately, you only see the steady state. So let's try to plot all these three together to actually see how they combine together. So I'm going to add a hold on such that every new plot keeps the previous plot. And I'm going to choose colors: red, cyan, and green. I'm also going to add a line width, 2. That is just to make the drawing line a bit thicker. That is my personal preference. It's not something that you're required to do in any way. So here you see the red, that is our transient solution, the green, that is the full solution, and the cyan, that is the steady state. So you see that the cyan and the green are different just at the very beginning, and then they pretty much match completely because the transient solution gets so small so fast.